For centuries, humanity believed the solar system was a private domain. Planets moved in predictable paths, comets returned on schedule, asteroids followed familiar rules. Everything belonged here. Everything was born with the sun. That assumption felt natural, comforting, logical. But the universe does not exist to make us comfortable. Beyond the gentle pull of our star lies a region of unimaginable violence, where newborn planets are flung outward, where giant worlds clash, where gravity becomes a slingshot capable of ejecting entire objects into the abyss between stars. These expelled remnants do not vanish, they wander. For millions of years they drift through interstellar darkness, cold and silent, carrying within them the fingerprints of alien suns. And one day, without warning, one of them crossed our path. In October 2017, astronomers scanning the skies noticed a faint object moving unusually fast. At first glance, it seemed routine, just another small body passing through the inner solar system. But when its trajectory was calculated, the equations refused to settle. The orbit was wrong. It was not bound to the sun. It was not returning. It had come from outside. For the first time in human history, we were witnessing an object that did not belong to our solar system at all. It was named ʻOumuamua, a messenger from afar arriving first. And first it truly was. ʻOumuamua was not merely another asteroid or comet. Everything about it challenged what we thought we knew. Its speed was extraordinary, far greater than objects native to our system. Its brightness fluctuated dramatically, suggesting a shape unlike anything previously observed, possibly stretched, possibly flattened, possibly both. At first, scientists assumed it was a comet. That would have been simple, comfortable, predictable. But there was no tail, no visible gas, no dust cloud. Then they assumed it was an asteroid. But asteroids do not accelerate without force. And yet ʻOumuamua showed a subtle push as it moved away from the sun, an acceleration that could not be explained by gravity alone. Something was propelling it. Radiation pressure was proposed. Exotic forms of ice were suggested. Hydrogen ice, nitrogen ice, substances that would sublimate invisibly. Each explanation stretched physics to its limits, but none could be dismissed outright. The object refused to fit neatly into any box. And that was the real shock, because ʻOumuamua was not just an astronomical curiosity, it was evidence. Evidence that other star systems form objects radically different from our own. Evidence that the Milky Way is littered with debris from destroyed or distant worlds. For the first time, interstellar space stopped being an abstract idea and became a tangible source of physical visitors. This was not science fiction. This was not speculation. This was direct contact, not with life, but with matter born around another sun. Yet humanity was unprepared. By the time we realized what ʻOumuamua truly was, it was already leaving. Our fastest rockets could not catch it. Our probes were grounded by time and technology. We watched helplessly as it faded into darkness, carrying its secrets with it. The realization that followed was profound and unsettling. If one interstellar visitor passed through unnoticed until after its closest approach, how many had come before? How many were passing through right now? How many would arrive tomorrow? The universe, it seemed, had been visiting us all along. We simply did not know how to look. And once we learned, the cosmos sent another traveler, one that removed all remaining doubt. If ʻOumuamua was a whisper, then the next visitor was a declaration. In August 2019, 2 years after humanity's first confirmed interstellar encounter, a familiar pattern emerged in telescope data. Yet this time, the universe was kinder. The object was detected earlier. Its path was clear. Its behavior was unmistakable. It was moving too fast to belong to the sun. Its trajectory was sharply hyperbolic, slicing through the solar system like a blade through still water. There was no ambiguity this time, no debate about classification, no hesitation. This object came from another star system. It would be named Borisov. Unlike ʻOumuamua, Borisov behaved exactly as an interstellar traveler should. It looked like a comet. It acted like a comet. It glowed, released gas, and developed a beautiful tail as sunlight warmed its surface. And that normality was revolutionary, because Borisov confirmed something critical. ʻOumuamua was not a fluke. Interstellar visitors were real, detectable, and diverse. Some were strange beyond imagination. Others were comfortingly familiar, yet still alien in origin. Spectroscopic analysis revealed that Borisov's chemistry was different from comets native to our solar system. The ratios of carbon monoxide to water were unusually high. The dust composition suggested formation conditions unlike those around our sun. This was not recycled solar system debris. This was pristine material from another stellar nursery. For the first time, humanity was not merely observing an interstellar object, we were studying one in detail. Telescopes across the world turned toward it. Space agencies coordinated observations. Borisov became a scientific celebrity not because it was mysterious, but because it was cooperative. It behaved. And in behaving, it told a story. It spoke of planetary systems where icy bodies form farther from their stars, of violent gravitational interactions that eject comets into interstellar space with tremendous force, of star systems that are not stable, not orderly, but dynamic and chaotic. In other words, it spoke of a universe that is far more active than we once believed. As Borisov passed through the inner solar system, it shed material, tiny grains of alien dust falling silently through space. Though none reached Earth intact, the idea itself was staggering. Particles formed around another sun had briefly joined our cosmic neighborhood. The boundary between air and out there had blurred. And then Borisov, like ʻOumuamua before, departed, destined never to return, continuing its endless voyage through the Milky Way. But something fundamental had changed. Astronomers now knew what to look for. Survey telescopes improved their algorithms. Detection strategies evolved. The sky was no longer just a map of familiar objects, it became a watch list for intruders. And the implications expanded rapidly. If 2 interstellar visitors were detected within just a few years, then statistically thousands must pass through the solar system over time. Most are small, most are dark, most go unnoticed. Some may have passed close to Earth long before humans existed. Others may arrive long after we are gone. Interstellar space is not empty. It is a vast archive of planetary history, drifting freely between the stars. And these visitors are not just scientific curiosities, they are samples. Samples of alien chemistry, samples of alien geology, samples of processes that shape worlds beyond our own. The realization sparked bold ideas. What if future missions could intercept such objects? What if probes could be launched quickly, using advanced propulsion systems, to rendezvous with an interstellar visitor while it passes through? For the first time, humanity could study another star system without leaving its own. Interstellar exploration, once thought to require centuries, suddenly felt closer. But as science celebrated clarity, a deeper unease remained. Because while Borisov fit expectations, ʻOumuamua did not. And nature rarely produces just one anomaly. The universe, it seemed, was hinting that not all interstellar visitors would be simple chunks of ice and rock. Some might be stranger, faster, older, and far more difficult to understand. Once Borisov confirmed that interstellar visitors were real and detectable, astronomers did something profoundly human. They looked backward, because science is not only about discovery, it is also about realization. Sometimes the universe reveals that it has been showing us the truth for decades, and we simply did not know how to interpret it. Hidden in old data, buried in dusty archives of telescope observations, were objects that no one had questioned deeply enough. Fast movers, odd trajectories, comets that did not behave quite right. These objects had been cataloged, labeled, and forgotten. But now, with new understanding, astronomers began to reanalyze them, and what they found was unsettling. There were candidates, strong candidates, that had entered the solar system long before ʻOumuamua, long before Borisov, possibly even long before the invention of the telescope. They had come, they had passed through, and they had left unrecognized. Some of these objects were initially classified as long-period comets, believed to originate from the distant Oort cloud, a spherical halo of icy bodies surrounding the solar system. But when their velocities were recalculated using modern models, a few refused to obey expectations. Their incoming speeds were too high, their orbits were too steep. Their paths suggested they were not merely loosely bound to the sun, they may never have been bound at all. One such object, detected decades earlier, showed a trajectory that could only be explained if it had entered the solar system already moving at interstellar speed. At the time, the error bars were large. The data was imperfect. The conclusion was postponed. Now, with ʻOumuamua and Borisov as benchmarks, the conclusion looked unavoidable. Interstellar visitors had been slipping past us for generations. This realization changed how astronomers viewed the Oort cloud itself. It may not be a closed shell of native debris. Instead, it could be partially contaminated, a graveyard of captured interstellar objects slowed down just enough to be trapped by the sun's gravity. In other words, the outermost reaches of our solar system may already contain relics of other stars, alien matter parked quietly at the edge of our cosmic backyard. And then there is the most unsettling implication of all. If interstellar objects have been passing through for billions of years, then Earth itself has almost certainly been struck by them. Long before humans, long before life became complex, possibly even before life began. This raises a question that blurs the boundary between astronomy and biology. What if some of the ingredients for life on Earth did not originate here? Interstellar objects carry organic molecules. We know this because comets within our solar system already do. Amino acids, carbon chains, prebiotic chemistry, all are common in space. Now imagine such chemistry formed around another star under different conditions, then delivered intact across light years of space. This is no longer speculation, it is probability. Some scientists now consider the idea that interstellar visitors may have contributed to the chemical inventory of early Earth. Not life itself, but the raw materials that made life possible. The universe, it seems, does not respect planetary borders. But interstellar visitors are not all slow drifters. Some arrive with terrifying speed. Modern simulations suggest that rogue planets, entire worlds ejected from their home systems, roam the galaxy in vast numbers. Trillions may exist in the Milky Way alone. If even a fraction of these worlds pass near other stars, they could scatter smaller objects ahead of them, high-speed debris moving far faster than typical comets. These hyper-velocity interstellar fragments would be difficult to detect and nearly impossible to intercept. Yet they exist. And that realization introduces a sobering truth. The solar system is not isolated, it is exposed, not constantly, not catastrophically, but persistently. The galaxy is alive with motion, with debris, with travelers crossing paths by chance. And as our detection capabilities improve, something becomes inevitable. We will see more, not one every few years, but many. Some small, some large, some familiar, some deeply strange. And perhaps one day one will arrive that challenges not just physics, but philosophy. Because the universe does not send the same message twice. As astronomers widened their search, they discovered something unsettling. The interstellar visitors we had already seen were not the fastest ones. They were merely the slow enough ones. The galaxy is filled with objects moving at extreme velocities, remnants of violent planetary systems, shattered worlds flung outward by gravitational chaos, and even debris accelerated by close encounters with black holes and supernovae. These objects do not drift gently. They tear through space. Hypervelocity interstellar objects move so fast that they spend only weeks or even days within the inner solar system. By the time telescopes notice them, they are already leaving. This explains a disturbing truth: most interstellar visitors are effectively invisible. Our detection systems were designed to track predictable orbits, objects that return, objects that linger, objects that belong. Interstellar travelers do not follow those rules. They arrive once. They do not slow down. They do not announce themselves. Some may pass between Earth and the Moon unnoticed. Others may cross the orbit of the Sun itself, only to vanish into the dark. Among the most extreme of these travelers are fragments accelerated by rogue planets. These planets, worlds ejected from their home systems, wander the Milky Way in staggering numbers. Each rogue planet acts like a moving gravitational weapon. As it passes through debris fields or near other stars, it scatters material ahead of it, creating high-speed projectiles capable of crossing entire star systems in a single pass. The solar system has almost certainly encountered such objects before, but we did not see them. And then there is an even more profound idea. Some interstellar objects may not originate from planetary systems at all. They may be primordial, formed in the earliest days of the galaxy, before stars fully settled into stable orbits, before planetary disks became orderly. These ancient relics would carry information from a time when the Milky Way itself was young. If such objects exist, and theoretical models suggest they do, then an interstellar visitor is not just a traveler from another star, it is a time capsule, holding clues to how matter behaved when the galaxy was still forming. This possibility transforms interstellar astronomy into galactic archaeology. Each object becomes a fossil, each trajectory a historical record, but speed remains the enemy. The faster an object moves, the harder it is to study. We see only a blur, a fleeting signature in the data. No close images, no spectroscopy, no second chances. This has led scientists to rethink exploration entirely. Traditional space missions take years to plan and decades to execute. Interstellar visitors do not wait. To study them, humanity must become fast, flexible, and daring. Concepts now exist for interceptor probes, small, autonomous spacecraft launched on short notice, capable of using solar sails, nuclear propulsion, or gravitational assist to chase down incoming interstellar objects. These missions would not orbit. They would not land. They would pass by at extreme speed, collecting data in minutes that could rewrite astrophysics. For the first time, we would touch alien matter while it is still in motion. But there is another realization that lingers beneath all this excitement. Interstellar visitors are not evenly distributed. They are more likely to arrive from certain regions of the galaxy, areas where stars are densely packed, where gravitational interactions are frequent, where chaos is the norm. This means that some star systems are more leaky than others. Our Sun may have already captured a few such objects, slowing them just enough to trap them in distant orbits. Some may still be out there, silent, frozen, waiting. Not every interstellar visitor leaves, some stay, and that raises a question with profound implications. If alien objects can be captured, what else can? When an object enters the solar system, escape is not guaranteed. Gravity is not just a gatekeeper, it is a hunter. If an interstellar visitor passes close enough to Jupiter, Saturn, or the Sun itself, its velocity can be altered. A slight loss of speed is all it takes. The object no longer leaves. It becomes bound, captured. This is not speculation. It is celestial mechanics. Astronomers now believe that the solar system may already hold interstellar objects in permanent residence, hidden among asteroids, comets, and distant trans-Neptunian bodies. They do not announce themselves. They do not glow differently. They simply exist quietly foreign. Some of the most intriguing candidates lie among the so-called Damocloids. Dark, inactive objects with comet-like orbits but no visible outgassing. Their trajectories suggest violent origins. Their chemistry is still largely unknown. These bodies may not have formed here. And then there are the strange objects orbiting far beyond Neptune, on tilted elongated paths that make no sense in the context of a neat, orderly solar system. Their orbits hint at past encounters, gravitational scars left by something passing through long ago. Perhaps a rogue planet. Perhaps an interstellar visitor. Perhaps something even larger. The idea that alien material may already be embedded in our solar system changes the entire search strategy. Instead of waiting for visitors to arrive, we may only need to identify the foreigners already living among us. But how do you recognize something that looks ordinary? The answer lies in isotopes. Every star has a unique chemical fingerprint. The ratios of certain isotopes, forms of the same element with different atomic weights, vary from system to system. These ratios are locked into the material during formation. If an object shows isotopic ratios that do not match the solar system's signature, its origin becomes clear. It did not form here. This technique has already been used on meteorites found on Earth. Most match solar system chemistry. A few do not. Those anomalies are still debated. But debate is the birthplace of discovery. Now consider the deeper implication. If interstellar objects can be captured and remain stable for billions of years, then alien material has been orbiting the Sun since before Earth formed. It has watched life emerge. It has watched continents shift. It has watched intelligence arise. And it has done so in silence. This idea reframes humanity's place in the cosmos. We are not newcomers to interstellar contact. We are late to the realization. But captured objects introduce another unsettling possibility. If natural objects can be captured, then artificial ones can too. This thought remains controversial, uncomfortable, and often misunderstood. But from a purely physical standpoint, there is no difference between natural and artificial matter when it comes to gravity. Anything with mass obeys the same rules. This does not imply intent. It does not imply design. It does not imply visitors with purpose. It simply implies openness. The solar system is not sealed. It is accessible. And as our instruments become more precise, the line between astronomy and archaeology continues to blur. Every unusual orbit becomes a clue. Every chemical anomaly becomes a question. The universe is not hiding its history. It is scattering it. Not all interstellar visitors remain in space. Some reach us. They arrive without warning, without ceremony, and without permission, slamming into Earth's atmosphere at speeds so extreme that physics itself struggles to keep up. These are interstellar meteors. Most meteors we see are familiar. They enter the atmosphere at speeds typical of objects bound to the Sun, tens of kilometers per second. They burn, flare, and fade, leaving behind fragments that tell a well-understood story. Interstellar meteors tell a different story. They arrive too fast. So fast that even the Sun's gravity could not have accelerated them to such velocities. Their incoming speeds exceed the solar system's escape velocity by a wide margin. This is the signature of an outsider. In 2014, sensors detected a fireball over the Pacific Ocean unlike any previously recorded. Its speed was extraordinary. Its trajectory was steep. Its energy release suggested a dense, resilient object. Years later, after careful analysis, scientists reached a startling conclusion. This object did not originate in our solar system. It came from beyond. For the first time, humanity had evidence that interstellar material had not just passed through, it had struck Earth. Fragments of that object may now rest on the ocean floor, scattered silently across the seabed. If recovered, they would represent the first physical samples of material formed around another star. Not observed, not inferred. Held. The implications are staggering. Because if one interstellar meteor reached Earth in recent history, then many more must have arrived over geological time. Some during the age of dinosaurs. Some during the rise of mammals. Some during the emergence of early humans. Alien material has been falling from the sky since before we could look up. Most of it burns away completely. Some of it survives, and when it survives, it becomes indistinguishable from local matter unless we know how to look. High-speed entry leaves unique signatures, extreme compression, unusual melting patterns, chemical anomalies locked into microscopic structures. These are not obvious to the naked eye. They require intention. They require suspicion. They require the willingness to ask an uncomfortable question. What if some meteorites in our collections are not from here? This idea transforms museums into archives of interstellar history. Every sample becomes a candidate. every anomaly becomes a potential message. Not a message written in language, but in physics. But speed is not the only difference. Interstellar meteors may also be older, far older, than any object native to the solar system. Formed around ancient stars that died long ago, these fragments may predate the sun itself. Holding one would be like holding a piece of pre-solar history. Matter older than our world, older than our sky, older than our name for the stars. And then there is the question science hesitates to ask too loudly. If natural interstellar objects can reach Earth, what about complex ones? This does not imply intention, it does not imply technology, it implies trajectory. The universe is dynamic, violent, efficient at moving matter across vast distances. Earth is not hidden, it is exposed to the galaxy. Yet this exposure is not a threat, it is a context. It tells us that our planet exists within a larger exchange of material energy and history. We are not isolated observers, we are participants. Every fireball streaking across the sky may carry more than spectacle. It may carry a story that began around another sun. The most important interstellar visitor may not have arrived yet. Or perhaps it already has, and we simply haven't recognized it. Modern astronomy is undergoing a quiet revolution. New survey telescopes now scan the entire sky repeatedly, night after night, building a living map of motion rather than a static picture of stars. This changes everything. Objects are no longer discovered by chance, they are tracked by behavior, speed, direction, acceleration, and behavior reveals origin. The Vera Rubin Observatory, once fully operational, will observe the sky with unprecedented sensitivity and frequency. It will detect faint, fast-moving objects that previous surveys would have missed entirely. Simulations suggest that once the system is online, interstellar visitors may be detected not once every few years, but several times per year. This means that ʻOumuamua and Borisov were not rare, they were early. The galaxy has been sending travelers all along, we simply lack the eyes to see them. Some of these future visitors will be small, meter-sized fragments passing close to Earth before burning up in the atmosphere. Others will be large kilometer-scale objects that can be studied for months as they pass through the outer solar system. And some will be strange. Not because they are artificial, not because they are intentional, but because nature is not obligated to repeat itself. Different stars produce different outcomes. Different planetary systems experience different forms of violence. Collisions, migrations, instabilities, each leaves behind debris shaped by unique conditions. We should expect diversity. Some interstellar objects may be rich in metals, others may be porous and fragile. Some may be ancient, irradiated by cosmic rays for billions of years. Each one will rewrite a small piece of astrophysics. But there is a deeper realization emerging. Interstellar visitors are not random with respect to time. They arrive in waves. As the sun moves through the Milky Way, it passes through regions of varying stellar density. Some neighborhoods are calm, others are chaotic, crowded with stars, debris, and gravitational turbulence. In denser regions, the rate of interstellar encounters increases. This means that Earth's exposure to interstellar material has not been constant over geological time. There may have been eras when such encounters were more frequent, periods when alien debris rain more heavily through the solar system, and those periods may correlate with events on Earth, not catastrophes, but subtle influences, chemical enrichment, organic delivery, isotopic anomalies that quietly altered the ingredients available to life. The universe does not act with intention, but it does act with consequence. As detection improves, humanity will face a new challenge, not scientific but philosophical. When interstellar visitors become routine, they will lose their novelty, they will become data points, and yet each one will represent a direct physical connection to another star system, a bridge across light years formed not by technology but by gravity. We will no longer ask, we will ask, what else has passed through? The galaxy will feel smaller, more intimate, less abstract. And then, inevitably, one visitor will arrive that defies classification entirely, not because it breaks the laws of physics, but because it exposes how incomplete our understanding still is. That moment will not signal danger, it will signal growth. Because every time the universe surprises us, it forces us to expand, not just our models, but our humility. The story of interstellar visitors is not about objects, it is about perspective. Not all interstellar visitors are solitary wanderers. Some arrive as remnants of events so vast that calling them objects feels insufficient. Across the Milky Way, stars live violent lives. They are born in crowded nurseries, dance with companions, steal material from neighbors, and sometimes die in explosions that briefly outshine entire galaxies. When such events occur, they do not merely destroy, they scatter. Debris streams are created, stretching across light years, composed of fragments accelerated to enormous speeds. These streams do not disperse quickly. They persist, coherent, moving through the galaxy like ghostly rivers. If the solar system crosses one of these streams, Interstellar encounters may spike dramatically, not one visitor, not too many. Some scientists believe that certain unexplained clusters of fast, moving objects detected in the past may be remnants of such encounters, moments when the sun passed through a region saturated with alien debris. This reframes randomness. Interstellar visitors may arrive in bursts, separated by long quiet intervals. Earth's geological and chemical history may quietly record these passages, layered like cosmic sediment. Then there are the most extreme travelers of all, objects accelerated near black holes. When a star wanders too close to a supermassive black hole, it is torn apart. Some of its material spirals inward, never to be seen again. But some is flung outward at incredible velocities, fast enough to escape the galaxy itself. These fragments become intergalactic travelers. They do not belong to any star system anymore. They do not belong to any galaxy. If one were to pass through the solar system, its speed would be almost inconceivable. It would not linger. It would barely interact. And yet, it would carry information from the most extreme environments known to physics. Matter shaped by gravity at its absolute limit. Even rarer are primordial interstellar objects, remnants from the early Milky Way, formed before the galaxy settled into its current structure. These objects would be chemically distinct, isotopically ancient, and physically altered by billions of years of cosmic radiation. They would be time travelers, not moving backward, but carrying the past with them. Detecting such objects would allow humanity to study galactic history directly, without relying solely on light and theory. But here is the crucial realization. The universe does not prioritize our convenience. Most extreme interstellar visitors will be small, fast, and dim. They will not wait for our telescopes. They will not announce their arrival. They will pass through silently. And yet, statistics is relentless. If something is possible, and the galaxy is large enough, it will happen. Again, and again, and again. The solar system is not an isolated island. It is a moving target, orbiting the galactic center, pulling through regions shaped by ancient catastrophes. We are swimming through history. Each interstellar visitor is a fragment of a larger story, one that does not center on us, but includes us nonetheless. And as our models improve, one truth becomes unavoidable. The list of known interstellar visitors is incomplete. Not because we lack intelligence, but because the universe has been far busier than we imagined. As the data accumulated, astronomers faced an unexpected problem. Not scarcity, but classification. Interstellar visitors do not arrive with labels. They do not declare their origin. They reveal themselves only through motion, chemistry, and probability. So scientists began assembling a list, not a simple catalog, but a hierarchy of confidence. At the top were the undeniable. ʻOumuamua, two-eyed Borisov. Their trajectories were unambiguous. Their velocities could not be explained by any solar system mechanism. These objects were not visitors in question. They were visitors confirmed. Below them lay a growing group of strong candidates. Objects with hyperbolic orbits detected decades ago, whose data quality was once insufficient but now looks increasingly persuasive. Reanalyzed with modern techniques, some show excess velocities that strain the assumption of solar system origin. These are not guesses, they are statistical outliers. Each one carries a probability, not certainty. But wait, and when probabilities stack up, they reshape understanding. Then there are the interstellar meteors. High-velocity fireballs recorded by military sensors, atmospheric monitoring systems, and all sky cameras. A handful exhibits speeds so extreme that even generous error margins cannot explain them as solar-bound objects. These are brief visitors, seconds long, but their implications are enormous. They suggest that interstellar material reaches Earth more often than anyone once imagined. But science is conservative by necessity. For every confirmed case, there are dozens that remain classified as possible or unlikely. Objects whose orbits appear hyperbolic at first glance, but whose uncertainties allow alternative explanations. These are the hardest cases, because they sit in the uncomfortable space between belief and dismissal. Reject too many, and you miss the pattern. Accept too many, and you dilute certainty. So astronomers do what science always does. They wait. They gather more data, they refine models, they improve instruments, and slowly the fog lifts. What emerges is not a neat list, but a gradient. A spectrum of confidence stretching from undeniable outsiders to ambiguous drifters. This spectrum itself is a discovery. It tells us that interstellar visitation is not rare, not exotic, not exceptional. It is continuous. The galaxy does not send visitors as singular events. It sends them as a background process, a steady drizzle of alien matter passing through every star system, including ours. The solar system is not unique in this regard. Every star experiences this exchange. Every planetary system is exposed to the debris of others. This realization erases a long-standing boundary in astronomy. The line between inside and outside the solar system was always artificial. Matter does not respect it. And as this list grows, confirmed, suspected, debated, it forces a new humility. We are not cataloging intruders, we are cataloging participants in a shared galactic ecosystem. Some objects will forever remain uncertain. Their data incomplete, their origins ambiguous. But uncertainty is not failure, it is an invitation to build better eyes, better models, better questions. Because the universe has already answered the most important one. Are interstellar visitors real? Yes, and they have been here longer than we have. The discovery of interstellar visitors has ignited a new era of exploration, one that challenges the limits of technology and imagination. For decades, space missions have targeted planets, moons, and asteroids, objects firmly bound to our solar system. But interstellar objects demand a different approach. They are fast, they are unpredictable, they are fleeting. Traditional mission timelines, years to decades, are simply too slow. To meet the challenge, scientists and engineers are designing new concepts, interceptor probes that can launch on short notice, equipped with advanced propulsion like solar sails, ion drives, or nuclear thermal engines. These probes would chase interstellar visitors, reaching speeds that rival the objects themselves. Imagine a spacecraft racing through the void at tens of kilometers per second, flying past an alien fragment formed around another star, capturing images, spectra, and dust samples in mere minutes. These missions are not science fiction, they are being actively studied. NASA, ESA, and private organizations have proposed concepts for rapid response missions capable of reaching interstellar objects during their brief visits. Sample return missions, once considered impossible for interstellar travelers, are now on the horizon with advances in miniaturization and autonomous navigation. But timing is everything. To succeed, these missions must be ready to launch within weeks of detection. This requires not only technological readiness, but also an evolution in operational mindset, flexibility, speed, and coordination. Alongside spacecraft, Earth-based observatories continue to advance. Next-generation telescopes will detect interstellar visitors earlier and track them longer, providing the data needed to plan intercepts. Artificial intelligence will play a role analyzing data in real time to identify candidates and predict trajectories. Together, these advances mean humanity is moving from passive observers to active participants in interstellar exploration. The next visitor may arrive at any time. It may be larger, brighter, or stranger than those before, and this time we will be ready. Because the universe does not simply invite observation, it demands interaction. Each interstellar visitor is an opportunity, a chance to touch matter born under alien suns, to learn not only about distant worlds but about our own origins, to bridge the gulf between stars with curiosity, courage, and technology. The story of interstellar visitors is just beginning. The question is no longer whether interstellar visitors exist, it is how humanity will respond. The arrival of ʻOumuamua and Borisov opened a door, one that leads to an uncharted future of cosmic encounters. But behind every discovery lies a deeper challenge to understand, to prepare, and to act. Scientists are now developing frameworks for rapid detection and response. Surveys are being optimized to spot fast-moving objects weeks or even months before their closest approach. Data pipelines are becoming more automated, with machine learning algorithms filtering billions of data points for telltale signs of interstellar origin. Yet detection is only the first step. Rapid mission design and deployment require international collaboration on an unprecedented scale. Space agencies, universities, and private industry are coordinating efforts to develop flexible spacecraft architectures. These spacecraft must be lightweight, highly maneuverable, and equipped with advanced instruments capable of capturing unprecedented detail in the brief windows available. Beyond physical exploration, interstellar visitors challenge our understanding of biology, chemistry, and even philosophy. What if such objects carry organic compounds, building blocks of life formed under alien conditions? What if their study reshapes our ideas about the universality of life? And on a broader scale, what does it mean for humanity to recognize that the cosmos is not empty, but a bustling marketplace of material exchange? These are not mere questions of curiosity. They touch the core of human identity and our place in the universe. As telescopes gaze deeper and probes fly faster, humanity is poised to become not just inhabitants of the solar system, but explorers of the galaxy. Every interstellar visitor is a messenger, carrying secrets from distant suns, waiting for us to listen. The journey has only just begun. Every interstellar visitor is a thread in the vast tapestry of cosmic history. They connect stars separated by unimaginable distances. They are relics of formation, destruction, and transformation. And in their silent journeys, they carry messages encoded in chemistry, structure, and motion. Some messages tell of violent origins, shattered worlds, close stellar encounters, and cataclysmic ejections. Others whisper of calm formation, icy bodies drifting slowly from distant stellar nurseries. But all share a common destiny: to cross paths with the sun The sun, a star like billions of others, becomes a gateway. Each encounter enriches our understanding. Each visitor is a teacher. And humanity stands at the threshold of learning from these cosmic emissaries. But the lessons go beyond physics and chemistry. They challenge our sense of isolation. They remind us that matter is shared. Stars exchange fragments. Planets exchange debris. And the solar system is a node in a grand galactic web. This interconnectedness invites reflection on origins, on life, on destiny. It asks us to reconsider boundaries, not just of space, but of thought. As we gaze upward, we must remember that we are participants in a dynamic universe. Interstellar visitors are not anomalies, they are expressions of cosmic communion. In studying them, we learn not only about distant suns, but also about ourselves. The galaxy is a vast ocean, and interstellar visitors are the ships that sail its currents. Each object is shaped by forces beyond human scale: gravity, radiation, magnetic fields, all acting over millions or billions of years. Yet despite their alien origins, these travelers share something familiar: the language of physics. They obey laws we understand, even as they challenge us to expand those laws. Some may be remnants of failed planets, others fragments of comets born around stars unlike our sun. Their trajectories are records of cosmic encounters, near misses, gravitational slingshots, and expulsions. By studying these paths, scientists reconstruct stories of distant star systems. But the stories do not end with astronomy. They ripple into other fields: planetary science, astrobiology, cosmochemistry. If organic molecules are found on interstellar objects, what does that mean for the origin of life? If materials unknown to Earth's geology are identified, how will that reshape our understanding of planetary formation? The discovery of interstellar visitors has opened a new chapter, a multidisciplinary quest. And it is a quest shared by all humanity, because these objects belong not to one nation, but to the universe. They challenge us to look beyond borders, to cooperate, and to embrace the unknown. The universe is sending us fragments of itself, and it is up to us to listen, to learn, and to explore. Looking ahead, the future of interstellar exploration is bright but challenging. Advances in telescope technology, spacecraft design, and computational methods promise to revolutionize how we detect and study these cosmic visitors. Projects like the Vera Rubin Observatory will scan the skies with unprecedented detail and speed, capturing faint, fast, moving objects that once escaped detection. At the same time, spacecraft propulsion is advancing rapidly. Solar sails, electric propulsion, and nuclear thermal engines offer the possibility of chasing interstellar objects at unprecedented speeds. Combined with artificial intelligence for real-time trajectory analysis, these technologies will enable rapid response missions that could reach visitors during their brief passage through the solar system. But technical hurdles remain. The window of opportunity to intercept these fast-moving objects is short. Coordination between international space agencies, private companies, and research institutions will be crucial. Ethical considerations will arise. What happens if we find organic compounds or even signs of life? How will humanity handle the responsibility of interacting with material from other star systems? These questions highlight the profound implications of interstellar visitation, not just for science, but for philosophy and culture. The universe is expanding our horizon, not only physically, but intellectually. Interstellar visitors are more than objects. They are catalysts. Catalysts for discovery, for cooperation, and for a deeper understanding of our place in the cosmos. The journey is just beginning. The story of interstellar visitors is ultimately a story about connection. It is a reminder that the universe is not a collection of isolated islands, but a vast interconnected web. Stars exchange material, planets exchange debris, galaxies exchange fragments. We are part of this cosmic exchange. Each interstellar visitor carries a piece of that greater story, a story written over billions of years across light years of space. By studying these visitors, humanity reaches beyond its origins. We bridge distances once thought insurmountable. We learn that the cosmos is not silent. It speaks in the language of trajectories, isotopes, and cosmic dust, and in listening carefully, we discover not only alien worlds, but the story of ourselves. This journey is far from over. With every new visitor, with every new discovery, we step further into the unknown. The universe invites us forward, to explore, to understand, to connect, and in doing so, we become more than observers. We become participants in a grand cosmic dance. The interstellar visitors will keep coming, and we will be ready, because the universe is vast and so is human curiosity.